Some reactions happen very quickly. For example, lighting off fireworks. And other reactions occur very slowly. For example, iron rusting, metal oxidizing. In kinetics, we're going to look at how fast or slow chemical processes happen. And kinetics, the study of kinetics, explains exactly how the reaction occurs, also known as the reaction mechanism. So far, we've looked at chemical reactions in fairly simplistic terms. We know that reactants, in order for a chemical reaction to occur, the bonds will have to be broken and new bonds are going to have to form. And in order for a chemical reaction to proceed in that manner, then the molecules have to come in contact with each other. They have to be able to come at each other not only with enough energy to break bonds and make new bonds, but also in the correct orientation. Molecules have to bounce off each other in just the right manner in order for a chemical reaction to occur, and with enough energy. So, the more homogeneous a mixture of reactants, the faster the molecules can react. Another factor that's going to affect a reaction rate is going to be the concentration of the reactants. In the image right here that we're looking at, steel wool being heated up and burned, the image on the left, you can see it's glowing and burning fairly well. The image on the right is burning with a lot more energy. The difference between the two is that this Erlenmeyer flask is filled with oxygen. What's the difference in the rate of the two reactions? This one's proceeding a lot faster because of an increase in concentration of oxygen in that reaction. The more oxygen molecules there are, the more they will collide with each other, and the faster the reaction will go. Temperature is also a factor that's going to affect the reaction rate. Higher the temperature, the higher the kinetic energy. The molecules are moving faster, they're bouncing off of each other more, and with greater energy. And catalysts, which are going to speed up the reaction rate without being used up in the reaction. And they do this by lowering the activation energy and changing the way the reaction proceeds. If we put two reactants together, hypothetically, reactant A and reactant B, initially all we have is reactant. And as time goes on, the two reactants, before reaction occurs, start to form products. So if we look at the concentration of reactants that we have at any given point in time, we can determine what the rate of the reaction is going to be. As time progresses, the concentration of the reactants is going to decrease as the concentration of products increases. Consider the reaction of butyl chloride with water, which is forming butyl alcohol and HCl. And the data table here shows the concentration of the butyl chloride, a reactant, measured over a period of time. So initially, at time 0, we're starting out with 0.1 molar butyl chloride. And as time progresses, the concentration, the molarity of the butyl chloride decreases until some point in time where it is completely consumed. And it's all gone into forming product. And we can look at the average rate of a reaction by looking at data obtained in a reaction and considering the change in concentration. For example, between time 0 and 50 seconds, and we look at the change in concentration divided by the change in time, that'll give us the average rate for the reaction at a given point in time. And as you can see, the rate of reaction as time goes on slows down. It slows down because the reactants are being consumed. As we have less concentration of reactants, we have less collisions among the molecules of the reactants, and the reaction slows down to the point where at least one of the reactants gets completely consumed. In most chemical reactions, we determine the reaction rate by looking at the change in the concentration, either of a reactant or the product, over time. We can calculate the rate of a reaction in terms of disappearance of reactant, or we can look at it in terms of appearance of product. And the units for average rates of a reaction are going to be moles per liter per second or molarity per second. Now, if we were to plot the concentration of the butyl chloride versus time, we would get a curve that looks like this. Starting at time equals 0, we're starting with our full concentration of butyl chloride, and as time progresses, the concentration decreases. As the reaction progresses, the concentration of the reactants is going to decrease. The concentration of the products is going to increase. And as it progresses, then the rate of the reaction is going to decrease. And we're going to get a curve like this. If we take the slope of the line, tangent to any point on the curve, that will let us look at the instantaneous rate at any point in time for a given reaction. And since all reactions slow down over time, the best indicator that we have of the rate of a reaction is what we're going to see happening here near the beginning of the reaction. Now, for this particular reaction, we have a 1-to-1 ratio all the way across. It's going to take 1 mole of the butyl chloride, 1 mole of the water to form 1 mole of the butyl alcohol, and 1 mole of the HCl. So, in other words, our reactants are going to disappear, get consumed, at the same rate that our products are appearing. So we would express that as rate is equal to the disappearance of, since the butyl chloride is disappearing, we're going to show it as a negative change. So the negative change in the concentration of the butyl chloride over the change in time. That's going to show us the rate of the disappearance of the butyl chloride. That is going to be equal to the rate of appearance of the butyl alcohol. So since it's being produced, we're going to consider that a positive change. Rate of appearance of the butyl alcohol is going to be equal to the change in concentration of the butyl alcohol over time. So we're looking at, once again, the rate of disappearance of reactant being a negative value is going to be equal to the rate of appearance of the product, a positive value. Now, in the event that the ratio is not a 1-to-1 ratio, as it is with this equation, we have a 2-to-1 ratio, then the rate of disappearance of the hydrogen iodide is going to be twice what the rate of appearance is going to be for either of the products, since we have 2 moles of this that are going to break down to form 1 mole of each of these. And so if we were to express that stoichiometrically, we would say that the rate of disappearance of the hydrogen iodide now is going to be a negative value. The rate of the disappearance, the change in the concentration over time, over the change in time, times 1/2. Okay? And the reason for that is that since this is disappearing at a rate of 2 moles compared to the rate of appearance of 1 mole for each of the products, this is disappearing twice as fast, or 2 times the rate of appearance of either the hydrogen or the iodine. And so that's going to be equal to the rate of appearance of the change in the hydrogen concentration over time, which is going to be equal to the change in the concentration of the iodine gas over the change in time. So, once again, the rate of disappearance of the hydrogen iodide gas is going to be double the rate of appearance of the two products. And so if we're showing that stoichiometrically, we're showing it as the disappearance, negative value, times 1/2, so that we have twice the change in time, or disappearing at twice the rate of the appearance of a hydrogen and the iodine. So for a generic equation with the lowercase letters signifying the coefficients in the equation and the uppercase letters signifying A and B as our reactants and C and D as our products, if we are to express the reaction and the disappearance of A and B to the appearance of C and D stoichiometrically, we're going to look at the, first of all, disappearance of A is going to equal to a negative value, it's disappearing, times 1 over the coefficient times the concentration of A over the change in time, which will be equal to the disappearance of B times 1 over the coefficient concentration of B over the change in time, which will be equal to the appearance of C at the rate of 1 over the coefficient times the concentration of C over the change in time, which will also be equal to the rate of appearance of D. So, if, for example, this were a 2 to 1 to 1 to 1 ratio, and we have a 2 down here in the denominator for the disappearance of A, that means that A is disappearing at twice the rate that B is disappearing at. Also, A is disappearing at twice the rate that either C and D are appearing at. Or, let's say this was a 1 to 1 to 1 to 2 reaction, then the appearance of D, if this is going to be a 2, is going to be at twice the rate as the appearance of C, and it's going to appear at twice the rate that B disappears, and it's going to appear at twice the rate that A disappears. Now, this data table shows us a variety of different experiment trials in a reaction and using different concentrations of either reactants and looking at the rate of the reactant depending upon the rate of the reaction dependent upon the differing concentrations of reactants. So if we take a look at, for example, experiments 1 and 2, okay? If you look at the concentration of ammonium between experiment 1 and 2, the concentration is doubled. The nitrite ion is held the same. There's no change in concentration for that. So whatever happens to the rate is going to be a reflection of the change in concentration of the ammonium, not of the nitrite, since we didn't do anything to that concentration. So what I can see happening here is that when the concentration of the ammonium doubled, the rate of the reaction doubled. Now if we look at experiments 5 and 6, in these two, the concentration of the ammonium is held constant, so we know that that's not going to have an effect on the reaction rate, while we're doubling the concentration of the nitrite ions. And so the effect of doubling the nitrite ions, nothing's changing here, so that's not affecting, is doubling the rate of the reaction. And looking at what happens when we manipulate the concentrations of either reactant to the rate will give us an indication of what's proceeding in terms of the components of the actual chemical process. And what we can see is that, first of all, rate is going to be, the rate of the reaction is going to be proportional to the ammonium ion concentration, and the rate of the reaction is also going to be proportional to the other reactant, the nitrite ion. So therefore the rate of the reaction is going to be proportional to the concentration of the ammonium ions times the nitrite ions. And if we write this as an expression, it becomes what's known as a rate law. And rate is equal to the rate constant. In this instance, K is going to be rate constant times the concentration of ammonium times the concentration, the molarity of the nitrate. So for a general reaction with a rate law, rate is equal to the rate constant, K, times the concentration of the first reactant raised to the power of, we'll say M, times the concentration of the second reactant raised to the power of, we'll say, N. And those exponents, M and N, are what we call reaction orders. It's important to realize that those reaction orders in a rate law are not dependent on the stoichiometric coefficients. We said that the rate law for the previous example was K is equal to, K times the concentration of the ammonium times the concentration of the nitrite ion. And since we have a presumed coefficient of 1 here, not coefficient, I'm sorry, since we have a presumed exponent of 1 here, we would say that this reaction was a first order reaction with respect to the ammonium and first order with respect to the nitrate. So the rule is, if you double the concentration and there is no change in rate, that would be considered a zero order with respect to that reactant. If you were to double the concentration of a reactant and the rate doubles, that would be first order with respect to that reactant. And if you double the concentration of a reactant and the rate increases by 2 squared, then that would be second order with respect to that reactant. Or if you tripled the concentration and the rate changed by 3 squared. So n squared, basically, whatever the coefficient for the reactant is, squared will give you the second order reaction. And typically we would see reaction orders of 0, 1, and 2 most commonly, although it is possible to have negative reaction orders in even fractions. And we can tell the overall reaction order by just adding the exponents. So since this reaction was first order with respect to the ammonium and first order with respect to the nitrite, we add that together, we get a second order overall. So here is another data table with 3 experiments and the concentrations of reactants and their rates. If we were to compare experiment 1 and 2, in experiment 1 and 2, the concentration of A is held constant. So I know that whatever is happening with the rate is not happening as a result of any change in concentration to A. But concentration of reactant B is doubled. Now, look what happened to the rate. Nothing. If you double the concentration of a reactant and nothing happens to the rate, then we would say that it was a 0 order with respect to that reactant. Now, if we look at experiments 1 and 3, in experiment 1 and 3, the concentration of B is unchanged, so I know that the concentration of A is what is causing the change in my rate. And as we double the concentration of A, the rate increases by a factor of 4, or 2 squared. So I would say that with respect to A, we are going to be a second order reactant. And so when we write the rate law for this, we would write rate is equal to the rate constant times the concentration of A squared times the concentration of B, which is a 0 order reaction, and since that is not affecting the rate law at all, or not affecting the rate at all, the concentration of B, then this would be our rate law for that particular example. Now we can take that rate law and we can use calculus to integrate it for the first order process. And it's going to look like this, where this is the concentration of the particular reactant at time 0, and this is the concentration of a reactant at some other given point in time, is going to be equal to the negative rate constant times T. And if we further rearrange that, we get this equation, which is in the form of a straight line. If a reaction is first order, really important, if a reaction is first order and you plot the natural log of the concentration of A, reactant A, versus time, you're going to get a straight line, and the slope of the line will be the negative K, or rate constant. If you consider the reaction in which methyl isonitrile is converted to acetonitrile, and you take a look at what has to happen to go from here to here, what's the difference? NC to CN. This little nitrogen right here has to split away from this carbon, and basically this little part of the molecule has to flip around to become acetonitrile. This is a first order reaction, a first order process, and these two compounds are isomers. which are just molecules that have the same atoms, but they're arranged slightly differently. So this reaction would be known as an isomerization reaction. Since we're looking at gases, we are going to graph the pressure of the reactant over time. And this is a typical curve. As the reaction progresses over time, the pressure decreases and decreases as the reactant gets consumed and more product is produced. Now, if we take these data and we instead graph the natural log of the pressure of the isonitrile over time, then we would get a straight line. And that straight line, if we graph the natural log of the pressure over time and get a straight line, then that will confirm that this is a first order process. And the K, the rate law constant for this reaction, will be the negative value of the slope of that line. If we integrate a rate law for a process that's second order with regards to reactant A, we would get this equation, which also gives us the form of a straight line, y equals mx plus b. And so, if we have a second order process and we plot the reciprocal of the concentration of A versus time and we get a straight line, then the slope of that line is going to be equal to the rate constant for that process, or K. Now this is the decomposition reaction of nitrogen dioxide. And if we're given an equation like that, and we take the information of concentration and plot that versus time a couple of different ways, we can tell by the graph whether it's going to be first or second order with respect to the nitrogen dioxide. So the two ways are first plotting it to see if it's a first order reaction. So we would plot the natural log of the concentration versus time. If that gave us a straight line, we would know that it was first order with respect to the nitrogen dioxide. But we don't get a straight line. So then we would try plotting the reciprocal of the concentration of the nitrogen dioxide versus time. And this time we get a straight line. That's the verification that we need to know that this process is going to be second order with respect to A. Half-life is a pretty convenient way of describing how fast a reaction occurs, especially if it's a first order process. Fast reaction is going to have a short half-life, and half-life is just the time that's required for the concentration of a reaction to reach 1/2 of its initial value, or the time required for 1/2 of a reactant to react. And we can use the first order reaction to derive this equation to calculate half-life for a first order process. Now half-life is pretty widely used in looking at radioactive decay, and that is the subject for another chapter. But in any case, for a first order reaction, the concentration of the reaction is going to decrease by half in each of a specific little time interval, hence the name half-life. Half-life is also important in medicine in determining the length of time that a particular medication would stay in the body. So we do use half-life for a few different uses. And the equation that we would use to calculate half-life for a second order process. Now a rate constant, K, is dependent on temperature, and in most instances as the temperature increases, so does the reaction rate. As we know, when temperature increases, kinetic energy increases, we have more collisions amongst the molecules, and that tends to make a reaction progress more rapidly.